Okay, so today we're going to start on the MIT final exam for one of their Calc 3 classes. Just found it online. So question 1 is find the equation of a plane P, which contains the line L given by x equals 1 minus t, y equals 1 plus 2t, z equals 2 minus 3t, and the point negative 1, 1, 2. Okay, so the strategy I'm going to use to solve this is basically I'm going to use this line to find two other points on the plane besides this one. And then essentially I'm going to solve for two vectors that lie within the plane and take the cross product of those two vectors to get a normal vector to the plane. And then I'm going to use the idea that the normal vector dot product with an arbitrary vector in the plane has to be 0. So let me kind of sketch out how I'm going to attack this problem first. So we have a plane. All right, we have a point and some line. Okay. Now, I could use the direction vector of the line, but it's simpler to just plug in two values for t, and plugging in two values for the t, we get two other points on the plane. And so, assuming that these 3 points don't lie on the same line, we can solve for two linearly independent vectors between these 3 points, and then taking the cross product of these two vectors, we'll get the normal vector to the plane. And once we solve for this normal vector to the plane n, I'm going to use the idea that if you have an arbitrary point on the plane like x, y, z, then basically, if you look at the vector, if we say we know this point x naught, y naught, z naught, right? They've given us at least 1 point. So we know some point on the plane. And then if we take a vector that's basically going to look like x minus x naught, y minus y naught, z minus z naught. If we take this vector, we know it has to lie on the plane, basically, because we've subtracted, if we look at like a three-dimensional coordinate system here, we've just taken this arbitrary point P on the plane and subtracted a different point that we know on the plane. And so the difference between these two vectors has to lie on the plane itself. All right. And so by that knowledge, we know this vector lies on the plane. So therefore, when I dot product it with the normal vector, I get 0. So, sorry, that's not the normal vector. But so we solve for the normal vector. Then I'm going to dot product this vector with the normal vector and set that equal to 0. And that will give me my equation for my plane in terms of x, y, and z. Okay. So normal vector dot product with this vector is equal to 0. So that's the kind of game plan of how we're going to solve it. And now let's go ahead and do it. So first things first, I'm going to plug in two arbitrary values of t. So plugging in t equals 0, we're going to get 1, 1, and 2 is in the plane. And then I'll just plug in t equals 1. And that'll give me 0, 3, and negative 1. Okay. And then, of course, we know negative 1, 1, and 2 is already in the plane. So now I'm just going to take two vectors, let's say v1, and I'm simply going to take, let's call this point p2, p3, and here's p1. So I'm just going to take, kind of arbitrary, but I'm just going to take p2 minus p1. You could subtract any two of these vectors, and you'd get a vector on the plane. So p2 minus p1, it's going to give me, let's see, 2, 1 minus 1 is 0, and 2 minus 2 is 0. So that one's pretty easy. And then v2, I'm just going to do p3 minus p1. Okay, so p3 minus p1, we're going to have 1 here. 3 minus 1 is 2, and then negative 1 minus 2 is negative 3. Let's see if I did this right. 1, 2, yeah. So these are our two vectors that lie on the plane. And so now I know geometrically if I take their cross product, I'm going to get a vector that's orthogonal to both of their directions, and therefore it'll be orthogonal to the plane. And so we'll have our normal vector. And so essentially, Yeah, essentially we're going to cross product these two vectors. So v1 cross v2. And this is going to give me 2, 0, 0, 1, 2, negative 3. So with this cross product, we can just set it up as the determinant of I, j, k, and then the first vector, second vector, and the rows. And this is kind of like a trick for evaluating the cross product, okay? So if I look at breaking down this determinant, I'm going to have I hat times, I can just write it out for y'all, so 2, negative 3, I hat minus 2, 0, 1, negative 3, j hat plus 2, 0, 1, 2, k hat, okay? And this determinant is just 0. We have a row of zeros, so this goes to 0. My j hat determinant is going to be 2 times negative 3, that's negative 6. Accounting for this negative sign here, we have a positive 6 j hat, and then a positive 4 here, so 2 times 2. And then obviously the off diagonal is going to be 0 in both cases. So this is plus 4k hat. And so I get that my normal vector, after all this work, my normal vector is just 0, 6, 4. Okay, and you can quickly verify that if you dot product this normal vector with with these two vectors, you're going to get 0 in both cases, right? This one is clearly going to be 0, and then the other one, you're going to get 12 minus 12, which will also give you 0. So that's a good sign, okay? All right, so the final step is to use the setup that I already described. So if we have an x, y, z vector within the plane, and then we already know some point in the plane, so I'll just use negative 1, 1, 2 is also within the plane. And basically, if I take the vector that's the distance between these 2 points, that vector has to lie in the plane. So I'm going to subtract this point from our arbitrary point, okay? So I'm going to get that x plus 1, y minus 1, and z minus 2 is a vector within the plane. All right, and so now I have an arbitrary vector within the plane. I'm going to dot product it with my normal vector and set that dot product equal to 0, okay? And geometrically, this looks like, again, I have a plane. I've started at this point P naught, which is, I've started at like negative 1, 1, 2, and then I've basically, I've basically looked at all other points everywhere in this plane and just looked at, you know, any possible vector that originates from this point and it can go anywhere else in the plane. Okay, so I'm basically covering the entire plane with this arbitrary x, y, z coordinate, and that's why this is going to give me the general equation for the plane, is because these x, y, and z are arbitrary. But the one thing that defines this plane is any vector on this plane will always have, if I look at the normal vector, the dot product with the normal vector will always be 0. And that's like uniquely what defines the plane, okay? All right, so let's do that. So final step, just going to set x plus 1, y minus 1, z minus 2, and I'm going to dot product it with 0, 6, 4, okay? And I'm going to set this equal to 0. So that's it. That's the equation of our plane. And then if we were doing this on the actual test, we might want to write it out. And so I'm going to have 6 times y minus 1 plus 4 times z minus 2 is equal to 0. And then if you wanted to further simplify, you could get 6y minus 6 plus 4z. And then we have a minus 6 and a minus 8, so we'd have a minus 14 is equal to 0. Okay. That's the equation of my plane. You can divide by 2 if you want. It's unnecessary, but anyways, that's the answer to this problem. So I'll see you for the next one.